Alright, so number 11. Number 11 is well, I think it's a neat problem. And here's why. Okay. So first off, in number 11, you have to realize you're given a graph of little h. Okay, cool, fine. Problem is, they ask you about big H of 8 minus big H of 4. Your first thoughts are, well, I'll just find the antiderivative. If I can find the antiderivative, I'll just plug in 8, plug in 4, I'll subtract them and I'll have the answer. There you go. What's the antiderivative? Right? And maybe you're thinking, I don't know, so you're like, well, I can find the, if I know the equation of this line, I guess you could do it that way, right? If you knew the equation of that line, you could find the antiderivative. We could do that. We could do the maybe we'll do that before this up. Find the equation of that line, do the antiderivative. Or if you connect this to an integral, if you say, you know what, big H of 8 minus big H of 4, that's weird, I've seen that. Yes, you have. That's the integral from 4 to 8 of little h of x. Those are equivalent. Okay, that's how you find this integral, is you'd say that equals big H of 8 minus big H of 4. Yeah. Now how does that help you? Well, how is that seen in a graph? That's just area from 4 to 8 under the curve. So you just gotta find this yellow area. And that's the answer to 11. And that yellow area ends up being 8. Okay, 12, 13, integral functions, and you're finding the derivative. These are the coolest problems because they're so, well, once you get the pattern, it's not bad. Okay, here's the quick and dirty formula, okay? First, step 1, realize that you're taking the derivative of an integral function. I can give you the coolest formula ever, but if you don't realize you're in a position where you need to use it, it's not going to matter. Okay, that's an integral function. Well, how do I tell? Okay, look at your limits of integration. Okay, they're x. Right, you got x up there. This is just, with respect to t. Now, how do I know I'm taking the derivative of it? Because they say so. Find the derivative of that with respect to x. Okay, Mr. Lund, so what if I'm asked to find the derivative of an integral function? How do I do that? It seems so hard because I have to do the antiderivative of this and plug in x and minus plugging in -5, and then I gotta do the derivative. No. Okay, derivative integral function. You got a couple things. Okay, you got a minus. And you got two pieces here. And you got, let's do a different color. You got two things here. You got two things over here. Okay, derivative of this guy. Not that guy. The derivative of that guy. He's going there. How much is it? Uno. Okay, derivative of that guy. He's going right there. How much is it? 0. Okay. That leaves me 2 spots. That leaves me this one and this one. Well, what goes in the yellow is that guy plugged into the equation, right, for t. So it's just sine 4 pi x. What goes in blue? Sine, not that it matters, it'll cancel out. 4 pi times -5. Okay, so you got, these are multiplications here. So you got this hunk of junk here. Take away the other one. That's your answer. Well, that goes away because it's times 0. How much is that? It's just sine of 4 pi x. Sine 4 pi x. Done. So now try it on the next one. Okay, but wait a second. H is like 4 plus integral function. Okay, well, what do we know about addition, subtraction when you're finding the derivative? Well, you can do them separately. So what's the derivative of 4? 0 plus. Okay, derivative of integral function. Okay, 1, 2, minus 3, 4. Okay, derivative of x squared. Okay, so the x squared stuff is going here. The negative 8 stuff goes here. Okay, so in one block I do x, that's 2x. That's going to be a 0. And if you plug x squared in, that's square root 2 plus sine x squared. Square root 2 plus sine a negative 8. Well, 0 times that goes away. Answer is 0 plus, so the answer is just 2x square root 2 plus sine x squared. Done. Next problem. Okay, that's derivative of integral functions. Okay, the last one, number 14. And I'm going to bed. Okay, we can do this. I'm given a graph of f. Pay attention to what you're given. Let's see what they ask me. A continuous function f is defined on the interval -4 to 3. Okay. I can kind of see that it's continuous, you know. Like, if you were going to sketch this curve, you wouldn't have to lift your pencil, but they tell me it's continuous. It doesn't look like it's differentiable, though, because you got that cusp there. I mean, not differentiable everywhere, just, you know, it's not differentiable at 0. Okay. Shoot. Back up. Back up. Okay. Continuous function is defined, the graph consists of 2 quarter circles. Okay. I spot the quarter circles. One of the quarter circles is that red thing. It looks like it's a quarter circle with radius 3. And then the other quarter circle is this one. It's a quarter circle with radius 1 because of that number. Okay, 2 quarter circles. And one line segment is shown in the figure. Let g of x equal. Okay, I got g of x. I'm going to rewrite it. Just up here, g of x. Wow, it looks like g of x is an integral function. Kind of interesting. Plus the integral from 0 to x of f of t dt. Okay. Find g of -3. And okay, so that's first goal. G of -3. So g of -3 equals 2 times -3 plus the integral from 0 to 3 of f of t dt. Okay, that's -6 plus, let's see, that's an area under little f. Do I have little f? Yes. From 0 to 3. 0 to 3. Okay, 0 to 3. So, I probably shouldn't have done those in the same color, right? I mean, 0 to 3 is, I mean, that the area I've shaded there, but, you know, that integral is going to do, you know, you kind of got some positives canceling out negatives, right? So that stuff all has negative area, and the stuff that I left in light blue has positive. Now, I think we're lucky because those two triangles have the same dimensions. which means that their area is going to cancel out. This has an area. This is 1.5 by 3. So 1.5 times 3 is 4.5, and then cut that in half, you get 2.25. I think we'll probably need that later. 2.25, and then the other one is negative 2.25, so that'll be plus 0. So the answer to this is negative 6. Now it says find g prime of x. Okay, let's erase this. Delete. Oh, how do I find g prime? It's okay. Look at g of x. G of x is this plus integral function. So what's the derivative of 2x? So g prime of x. Derivative of 2x is 2. What's the derivative of, oh, integral function? How do I find the derivative of integral function? Well, you're going to go the derivative of the upper bound. Yikes. Derivative of the upper bound. Derivative of x is, derivative of upper bound is 1 times the upper bound plugged in. Well, that's just f of x minus derivative of the lower bound, 0 times the lower bound plugged in, f of 0. So that guy goes away. G prime of x is 2 plus f of x. Well, how much is g prime of negative 3? Okay, g prime of negative 3 equals 2 plus f of negative 3. Well, you're looking at a graph of f. F of negative 3, negative 1, negative 2, negative 3. F of negative 3 is 0. So 2 plus 0 equals 2. So I got g prime. I'm going to probably need that. Put that guy over there. And that was my answer to g prime of x. So I got that. Okay. Next question. Delete. Determine the x-coordinate of the point at G, which G has an absolute maximum from negative 4 to 3. Okay. Well, what do we know about the derivative? Because we're going to definitely use, we're going to use the derivative to help us determine when the absolute maximum is. And it's from negative 4 to 3. So we're going to kind of think about this. Let's see. You're going to get a the first time I did this problem for an absolute max, I checked, if you check that, you want to check the endpoints and then your critical values. So your endpoints would be negative 4 and 3, and then your critical values are going to be wherever your derivative is 0 or undefined. So that's one way to do it. So your absolute max, you'd want to check g of, and you're maximizing g, so that's why it's g of negative 4 equals g of 3 equals, and then let's see, where does g prime of x equal 0? G prime of x equals 0 when 2 plus f of x equals 0. So when f of x equals negative 2. Okay. So is there anywhere on the graph where f of x is negative 2? Okay. So right here, f of x is negative 1. Then f of x is 0. Then f of x goes all the way up to 3. Then f of x goes to 2. I'm just looking at the y values on the curve. Right, those are all f of x. So where is f of x negative 2? Right there. At that point. Now, is f of x ever undefined? No. So you just have to look at, we're just looking, where's f of x negative 2? So what's the x value there? That's what we need. Well, we know the equation of that line. I mean, you could probably just estimate it and you'd be fine. It looks like 2.5. But let's say you weren't sure. Well, the equation of that line, it's got, let's see, y equals the y-intercept of 3 plus the slope of down 1. I gotta find, let's say, down 1, down 2, down 3, down 4, down 5, 1. Oops. Try that again. Delete. So if I do rise over run, I rise down 1, 2, 3, 4, 5, 6, and I run over, let's see, 1, 2, 3. I'm just linking that point and that point. So down 6 over 3, that's a slope of negative 2. Negative 2x. So you're wondering, when does y equal negative 2? So you'd have negative 2 equals 3 minus 2x. So that would be negative 5 equals minus 2x. X equals 2.5. So you want to check g of 2.5. Wait, what was he doing? Okay, absolute extrema. You check your end values and your critical points. Your critical points are where your derivative is 0 or undefined. Our derivative never went undefined, right? How do you, what was the derivative? Okay, you're maximizing g. So you need the derivative of g, which happened over here. G has a pretty cool derivative. It's just 2 plus f of x. So g prime is 2 plus f of x. So in order to look at where g prime is 0, you look at where 2 plus f of x is 0. Which 2 plus f of x is 0 when f of x is negative 2. And you have the graph of f. So just look at the graph of f to look at when it's negative 2, it happened at that red dot, and away you go. So you got to compute those values. So g of negative 4. Well, remember what you did in A? You determined g of negative 3. That was just like an area problem. So we can do that. G of negative 4. Okay, g of negative 4 equals 2 times negative 4 plus the integral from 0 to negative 4. Oh, that's weird. I'm integrating left to right. Okay, f of t dt. If you didn't catch that, I was commenting on, you're going from 0 to negative 4. That's left to right. So 0 to negative 4, you're probably thinking, oh, well, that's this stuff, and it's this stuff. Yeah, but if you're integrating from left to right, 0, 0 to negative 4, the stuff above the x-axis is going to be negative, and below is going to be positive. So you need to determine, well, what's the area of the orange stuff? I know that's going to be negative because I'm going to the left. So that's a quarter circle. So 1/4 pi r squared, and the radius is 3. So 1/4 pi 9 times 9. And that's negative. And the red will be positive because it's left to right, or right to left. So the radius is 1, and it was a quarter circle. So that's 1/4 pi times 1 squared. So you got negative 9 pi over 4. That's negative 9 pi over 4, and then this is pi over 4. So we got g of negative 4 is, okay, negative 8 minus, because it's negative 9 pi over 4, minus pi over 4. Let's see, 9 pi over 4 take away, or sorry, that was a plus pi over 4. We said it's positive area. So negative 9 pi over 4 and positive pi over 4 is negative 8 pi over 4. So negative 8 minus 8 pi over 4. Negative 8 take away 2 pi. Negative 8 take away 2 pi. So that's obviously a pretty big negative. So now we need to compute g of 3. Same principles will apply. G of 3 equals 2 times 3 plus the integral from 0 to 3 of f of t dt. Okay, so that's 6 plus, let's see, 6 plus, okay, now we're going to find an area, right? So from 0 to 3. Okay, there is 0, there is 3. That's positive area, because you're going left to right. That's negative area. We said they canceled out, so 6 plus 0, that's just 6. And then 2.5. 2.5 says g of 2.5. Do this all over. Delete. Oh, we're almost there. G of 2.5. G of 2.5. Okay. So go back to function g. It was 2 times the input times the integral, or plus the integral from 0 to the input, ft dt. Okay, that guy is 5 plus, okay, 0 to 2.5, 0 to 2.5, 0 to 2.5. Okay, so that's this stuff here. 1.5 to 2.5. Okay, and then 2.5 is here. So this stuff. So the red will be positive because you're going left to right. The blue will be negative. Okay. So the red has an area of, I think we already calculated it earlier. It's just a triangle, 3 by 1.5. So 2 1/4, 2.25. And then the blue is well, we know that that's 1.5 and that's 2.5. So the blue is 1 by 2, I believe. So we just got to make sure, is this intersection point here correct? Well, I think we had the equation of that line. It was y equals 3 minus 2x when x is 2. Let's see, 1, 2. Yeah, when x is 2, how much is y? When x is 2. All right. Oh, sorry, that's when x is 2.5. 2.5. Oh gosh. 2.5. So we're trying to find this y value of that coordinate right there, because I need to know the height of that triangle. So that's 2.5, comma, okay, 3 minus 2 times 2.5 is 3 minus 5, so that's negative 2. Okay, so that blue triangle is definitely 1 by 2. So 1 times 2 is 2, cut that in half is 1. So that blue triangle's got an area of negative 1. Okay, negative 1. So you got negative 1, 2 1/4. So what we had? 5 plus negative 1 plus 2.25 is 6.25. Ding ding ding, we have a winner. We have a winner. The absolute max is at x equals 2.5. your justification is this stuff here. So absolute max of 6.25 at x equals 2.5. Okay, we're so close. So now we need to know when G has an inflection point. Well, so a couple ways you can go about that. So inflection points deal with change in concavity, right? So maybe you want to talk about, generally we look for mins and maxes of the first derivative, or where your second derivative crosses the x-axis. So one thing you know is g prime of x is equal to 2 plus f of x, which means g double prime of x is, the derivative of that is 0 plus f prime of x. So g double prime is f prime of x. So think, where would, we're looking for g double prime crossing the x-axis, right? If g double prime crosses the x-axis, there will be an inflection point. Well, g double prime will cross when f prime crosses. They're the same thing. So think up here. We want to think, when would f prime cross the x-axis? Okay, so that's f. How would I know when f prime crossed the x-axis? Okay, well, oops, f prime crosses the x-axis. You kind of have to talk your way through these ones. Okay, if that's f, where does f prime cross the x-axis? Alright, well, how is f prime related to f? Well, it's the slopes. Okay? It's the slopes. So, oops. I really have to talk myself through this one because it's just about 11 o'clock and it's getting hard to think straight. But I can't even find the page here. Okay. So g double prime of x is f prime of x. We're looking for crosses x-axis, and we know g prime of x equals f of x. And we're looking for, if you were going to use that model, you'd be looking for the mins and maxes. But I think you're with me if I say, hey, if the second derivative crosses the x-axis, then we have an inflection point. So let's just look for where f prime crosses the x-axis. So keep in mind you're looking at f. So let's see. You got a 0 slope here, then you have positive slopes, then you have a 0 slope here, and then you have negative slopes. Yeah. So you have a 0 slope, and you go to positive slopes, and you go to a 0 slope, and you go to negative slopes. Now, if you were gonna, sketch a graph of f prime, we'll just overlay it. We can do it in red. That's fine. So you have a 0, we'll do it in It's a thick marker. 0 here, 0 here. Your slopes, let's see, they get, well, they go from 0 to positive back to 0. So they start out getting positive, slowly get positive, and then they start to quickly get very positive. So they get really positive. Yep, and then they start to get, so they max out positive slopes, and then they start getting less positive. Okay, so they start actually getting less positive in this range right in here. So let's say that that's the max positive slope, and then it goes back down. So let's see. And it's going to go down. Okay, so we're sketching F prime, and then right away the slopes go negative, and they're like a negative. They're a negative constant. So then you might, let's say those slopes were all, well, I think we did say what they were. It was -2. So that's your curve. And now you're going, wait a second. If that's my curve, do I count that as an inflection point at x equals 0? Do you count that as an inflection point? This is kind of a tricky question, and you have to think back to, okay, what does it mean to be an inflection point? Okay, I promise we'll do this, then I'll shut up and we'll be done. Okay, inflection point. Concavity changes, and you can draw the tangent line. On your graph. I think you're going to all agree concavity changes. Now when I say on your graph, that would be like on your graph on the graph of your the original function, not the second derivative, not the first derivative, but the original function. So I'll let you think about that one. Does that thing there indicate an inflection point? So good luck. Thanks for sticking with it. And we can talk about it more in class.